All right, welcome everyone. So, in our past lectures, we've really spent a lot of time digging into derivatives, right? We got really good at finding that instantaneous rate of change to figure out things like marginal cost and marginal revenue. Well, today we're going to flip that entire concept on its head and explore its inverse, integration. And I want to be clear, this is not just some abstract math problem. Integration is the tool that lets us go from that very specific next unit analysis back to the big picture. We're talking total cost, total revenue, and of course, total profit. Getting a handle on this is absolutely essential for any kind of strategic business decision, whether you're setting prices or doing long-term financial forecasts. So let's start with a scenario that I guarantee many of you will run into as managers or analysts. Imagine your operations team comes to you with this beautiful, perfect data on your marginal cost. You know exactly what it costs to make just one more widget at any point in your production run. Now, that's incredibly useful for making short-term decisions. But then you have to take that data to the board of directors, and they're going to ask a totally different question. They don't really care about the cost of the next unit. They need to know the total cost function. Why? Well, think about it. Without that total picture, how can they set the right prices? How can they possibly forecast the quarterly profits? They can't make those critical budgeting decisions for the whole company. So how do you get from the marginal to the total? That's the problem, and integration is the solution. So here's our game plan for today. First, in section 1, we're going to formally lay out this manager's dilemma so we're all crystal clear on the business problem we're solving. Then, in section 2, we'll get into the mathematical theory, defining integration as reversing the derivative. Section 3 is where we get our hands dirty and build your integration toolkit with the key rules you'll need. Then, in Section 4, we'll actually apply those tools to our marginal cost problem step by step. And finally, Section 5, and listen, I really can't overstate how important this last part is, we're going to uncover the crucial business meaning behind what looks like a tiny mathematical detail, that constant of integration. All right, let's dive right in with section 1, the manager's dilemma. What we're really talking about here is making that critical jump from the tactical day-to-day analysis of the next step to that strategic big picture view of total costs or total profits. That's the perspective the C-suite needs to make informed decisions. This is a perfect analogy to get our heads around this. You're all pros at derivatives by now. You know that if you have a function for the total distance you've traveled, taking the derivative gives you your speed at one precise moment. It's your speedometer, right? Well, integration does the exact opposite. Imagine all you have is a detailed log of your speed at every single second of your trip. Integration is the process that lets you take all of those little snapshots of speed and add them all up, accumulate them, to figure out the total distance you traveled. So in business terms, if a derivative gives us the marginal cost, the speed at which costs are rising, then the integral lets us find the total cost, the total distance our costs have traveled. It's all about accumulation. Okay. So with that concept in our back pocket, let's move into section 2. We're going to get a little more formal now and give this idea of reversing the derivative its proper mathematical name, the indefinite integral. Okay, what you're looking at here is the formal definition. The indefinite integral, or as it's also called, the antiderivative, basically asks one simple question. What original function, which we'll call capital F of x, would I have to differentiate to end up with the function I started with, little f of x? But, and this is a really fascinating detail, there's a catch, and it's all about that plus c. Think about it for a second. The derivative of x squared is 2x. Simple enough. But what's the derivative of x squared plus 5? It's also 2x. What about x squared minus 100? Still 2x. You see, since the derivative of any constant is just 0, there isn't just one single answer. There's a whole family of functions that could be the right antiderivative. And that's exactly why the result of an indefinite integral always has that general constant, the plus c, tacked on at the end. So this leads to a really important realization. The good news is, we don't have to just guess what these antiderivatives are. Nope. Mathematics gives us a clear, reliable set of rules, our integration toolkit. Let's move into section 3 and build that toolkit right now. And let me tell you, mastering these rules isn't optional. It's absolutely fundamental to doing any kind of serious business analysis. These 3 rules you see here, these are the absolute workhorses of integration in business and economics. You're going to use them all the time. Let's break them down. First, the constant rule. Super simple. The integral of any constant, k, is just kx plus c. So the integral of 7 is just 7x plus c. Easy. Second, and this is the big one, the power rule. You will use this constantly. To integrate a variable raised to a power n, you just increase that exponent by 1, and then you divide the whole thing by that new exponent. So the integral of x squared becomes x cubed divided by 3. Makes sense, right? Finally, we have the sum rule. This is basically our divide and conquer rule. It just says that if you need to integrate a bunch of things added together, you can just integrate each part separately and then add all the results up at the end. It's what lets us break down complicated problems into simple, manageable pieces. All right, section 4. This is where the rubber meets the road. It's time to take all this theory and put it into practice. We're going to move away from the abstract rules and into a real, concrete business application. We are going to walk through the entire process of finding a total cost function from a marginal cost function. Okay, so put on your financial analyst hat. Your company's ops team has done their homework, and they tell you that the marginal cost to produce your product is modeled by the function MCX equals 2x plus 10, where x is just the number of units you make. This kind of linear function tells you that the cost of making that next unit goes up at a steady rate. Maybe you have to start paying overtime or your machines work less efficiently. Now, management sees this and they say, great, but we need the bigger picture. What is our overall cost structure? We need the function for our total cost, CX. Your job is to find it, and your tool is integration. So we're going to follow these steps to the letter and use our toolkit to solve this. Step 1, we set up the problem. The total cost C of x is going to be the integral of our marginal cost, 2x plus 10. Step 2, right away, we use our divide and conquer strategy, the sum rule, to break this into two easier integrals, the integral of 2x and the integral of 10. Now for step 3, we focus on that first piece, the integral of 2x. We use the power rule here. The power on x is just 1, so we raise it to 2 and then divide by 2. For step 4, we handle the second piece, the integral of 10. That's a simple application of our constant rule. And finally, in step 5, we'll put the pieces back together and see what our complete general total cost function looks like. And after all that, here's what we get. C of x equals x squared plus 10x plus c. The integral of 2x is x squared. The integral of 10 is 10x. But hold on, look at that. There it is again. That unknown piece of the puzzle, that general constant of integration, plus c. Now, mathematically, this is the correct general answer, but from a business perspective, this function is basically useless as it is. It's not one cost curve, it represents an infinite family of possible cost curves. To use this for real financial planning, we have to nail down the specific value of c. And this question right here brings us to the most important concept in this entire lecture. What exactly is this plus c when we're talking about business? Why can't we just, ignore it? And let me be absolutely clear about this. This is not some minor mathematical detail. In the world of business, that constant of integration has a very specific, a very real, and an absolutely critical meaning. And that brings us to our final section, section 5. Forgetting about the constant of integration is, without a doubt, the single biggest conceptual mistake students make on exams. And its real-world meaning is the perfect example of why you have to understand the business context behind the math. We're about to use this little constant c to uncover your company's fixed costs. In mathematics, anytime you want to solve for a specific constant like c, you need what's called an initial condition. You need one known data point to anchor your function in reality. Well, in a business cost problem, that initial condition is your fixed cost. Think about what fixed costs are. They're the expenses you have to pay even if you produce absolutely nothing, 0 units. They are completely independent of your production level. We're talking about things like rent for the factory, your insurance payments, the basic utility bills, and the salaries for your admin staff. These are the costs you have at a production level of x equals 0. So here's the big reveal, the key insight. That constant of integration, c, is your total fixed costs. And we can prove it very simply. Let's take our general cost function, c of x equals x squared plus 10x plus c. Now let's see what happens when production x is 0. We just plug in 0 for x. So c of 0 equals 0 squared plus 10 times 0 plus c. Well, the first two terms just vanish. And what are we left with? C of 0 is equal to c. Therefore, by definition, the constant of integration must be the fixed cost. So let's say we go talk to the accounting department, and they tell us, yep, our fixed costs are $5,000 a month. We now have our initial condition. This means we know the specific value of our constant. C is 5,000. And just like that, we have found the final missing piece of our financial model. And here it is, our final beautiful result. C of x equals x squared plus 10x plus 5,000. This is no longer some vague general formula. This is a complete, specific, and totally actionable model of our company's total costs.
With this function, a manager can now accurately predict the total cost of producing any number of units, and that is incredibly valuable for things like setting prices to guarantee a profit, finding your break-even point, and running all kinds of what-if scenarios to maximize your profit.
I really want this quote to stick with you because it's the most important takeaway from today. If you go into a meeting with your CFO and you present a cost model but you've forgotten the plus C, you haven't just made a small math error. You have built a model that completely ignores every single fixed cost your company has. You're basically telling them it costs $0 to even open the doors in the morning. That is a fundamentally flawed analysis, and it could lead to absolutely disastrous business decisions.
So as we wrap up, I want to leave you with one last thought, just to really highlight how powerful and versatile this tool is. We focused entirely on cost today, but this exact same method works in other critical areas of business. If you have a function for marginal revenue, guess what? You can integrate it to find total revenue. If you have the marginal profit, you integrate it to find total profit. The applications for this are everywhere in strategic business analysis, and I promise you, mastering this tool is going to serve you incredibly well in your careers.